I actually tell people, if there is one thing that people remember about this, is that the output of the LLM is untrusted input into your system. So you need to treat the output of any LLM as if it came from an untrusted source.
Once you realize how vulnerable AI is to an attack, once you realize how it can pretty easily be made to do things that it shouldn't, you're probably wondering, is there any way to defend against these attacks? And the answer is yes, but it's not simple. Donato is about to walk us through a multi-layered defense framework that ReverseSec have developed for securing AI applications. Think of it like security at an airport. You don't rely on just one checkpoint. You need multiple layers of protection, each catching different types of threats.
So what you see now on screen, I call it the LLM Application Guardrails, and this is what good looks like. Now, in an LLM system, in an LLM application or use case, you have different stages at which different types of guardrails can be implemented. And typically, you have to mix and match at these different layers, these guardrails, to get the security that you're looking for. Now, typically, there is guardrails that are baked into the LLM itself. So this would be the creator of the LLM, let's say OpenAI, that's doing the training, that essentially bakes guardrails inside the training data set or the training methodology. And this is typically very related to generation of illicit or harmful or content, and they try to make it less likely for the LLM to engage into that. Then as a developer, so as an organization that consumes an LLM to build a use case, there is a lot that can be done from the prompt engineering point of view. So what you see here are some of the techniques. So obviously prompt engineering is how we program the LLM, how we get the LLM in our application to do exactly what we want it to do. And there are prompt engineering techniques that can reduce the attack surface, that can make the LLM more aligned to what we're looking for and less susceptible to attacks like the one that I showed you before with a prompt injection. So for example, there is something called data spotlighting, which allows the LLM to kind of better distinguish what is data from what's an instruction. So in the example that we saw before, the email sent by the attacker, that's data. It should never be considered an instruction, but as you could see, the LLM got confused and followed the instruction in the data as if it was coming from the user. So spotlighting is a technique which will make that a little bit harder. It doesn't completely resolve that, but it makes it harder. And then there is input and output checks. So these are, again, outside of the LLM. So typically, we can look for common patterns of jailbreak and prompt injection attempts. And again, this is not fully deterministic, but you can at least remove what is known to be bad.
What Donato is showing us here is the actual process of securing an LLM. First, you have the foundation models, and they train security into the AI itself. Then, developers add their own layers. First, carefully engineering prompts that help the AI identify malicious instructions. And then, there are input filters that catch known attack patterns and output validations that check everything the AI produces before it takes any action. And this isn't theory. These are the technical actions being implemented by senior security researchers for paying clients today.
And then you have topic guardrails, which might apply. So for example, if you have a financial chatbot or a customer support chatbot for a company, you want to make sure that it stays within certain topics so that the users can't just go to that chatbot and ask whatever. And so this is what's called a topic guardrail. And then you have harm categories. Now, this is a very big and difficult category because it basically looks at prompts or inputs into the system that might be trying to elicit illegal content, harmful content. So typically people say, tell me how to make a bomb, but that's an example. Like it could be, tell me how to do insider trading. And so they try to look at intent and try to reduce or detect prompts that are malicious. And that's the same on the output. So I actually tell people, if there is one thing that people remember about these, is that the output of the LLM is untrusted input into your system. So you need to treat the output of any LLM as if it came from an untrusted source. So there is a lot of validation that your system needs to do. And this validation is typically very contextual to what you are doing in that particular use case. For example, are you expecting in your use case that the LLM would produce a URL? And are you expecting URLs to foreign domains? Or are you only expecting certain data formats and certain contents that you can filter for? So there is a lot of stuff that can be done here, like harm categories, again, checking for harmful content, hallucinations, trying to reduce that. And then moving into the agentic AI, there is that access control enforcement. So when LLMs can do things, we were talking about MCP, talking about skills. The way those skills are authenticated and authorized is fundamental. There needs to be users oversight, but there needs to be controls around it, which try to sandbox these operations that the LLM can execute, typically on behalf of the user. And there are many ways that people can implement these. We're not going to go into the technical detail, but these kind of controls can typically be implemented with classifier models, embeddings, LLM judges, or even more traditional cybersecurity controls. So again, when you look at these, if you're building like an LLM application, our use case in your product, you are going to need a mix of all of these together in order to be able to secure your application. Give you an example of something we worked on a couple of weeks ago. So our customer basically wants to automate some of the first line customer support. So there is an email that comes in, and then the customer has built like a workflow where this email is fed into an LLM, and then they look for similar emails that came from other customers that potentially had the same problem, and then feed like the top 5 most common or most similar tickets associated for many customers associated to that particular problem into the LLM, and they tell the LLM, listen, this customer has just sent this email. We found these 5 tickets that have been closed, which we think are similar. Based on this, can you give a response? And then the LLM says, yes, I can give a response, or this should be escalated. If the LLM gives a response, they automatically send an email back to the user. Now, this sounds pretty normal, but what we demonstrated is that I can send an email where I can get the LLM in its response to tell me the information, personal information about the other users that he knew, like those 5 tickets and all the resolution that was done. I can get the LLM to tell me information about all those other customers, including names, what they asked about, and what their resolution was. So by doing that, I then can get that information out, and then I could target those users. I could call them with a lot of knowledge, and they would pretty much think that I am the company, and then I could probably, do some social engineering attacks on them. So a lot of it has got to do with data exfiltration, or getting the LLM to produce something that in that context makes sense.
A company might build an AI to help their customers do something faster, but a single malicious email can expose the personal information of other customers regardless of how secure that data is. And this isn't hypothetical. ReverseSet demonstrated this attack just a few weeks ago. So how do developers actually test whether their guardrails are working?
So let's say you have an agent. So you have an LLM that can do something. The rule is any entity, anybody who can control a tiny bit of what goes into that LLM can potentially take over via one of these prompt injection attacks, can potentially take over the LLM, can make it respond or produce actions or call APIs the way they want. Not just the user, but anybody. If the user takes a document, a file, anything, a web page, any of those can contain an attack. So all the input into the LLM is potentially problematic, and all the output is potentially untrusted. Now, this is the golden rule. And then what you see on the screen is what people need to be doing when they are implementing. So obviously this is for developers when they are implementing applications. When you are using an application, you need to be very careful what data you give it access to, essentially, because that's and what actions it can do on your behalf. And I always want to look, especially on the action side, I think it is really important to have a degree of validation from the user. So I do not want the LLM to be creating files on disk, especially outside a very sandbox directory, or I don't want the LLM to be running arbitrary commands. This is very common now in all of these coding editors, all of these coding agents. I don't want them to create files or run commands unless I can very quickly verify, okay, this is the files you want to create. And especially the commands, I want to check the commands that the LLM wants to run, because they could be wrong to start with, not an attack. They could just be very, very wrong. Could delete an entire production database if you're not careful, right? We know those kind of things. But obviously, if there is any file in your developer workspace or any library which might potentially have been poisoned with an attack, once that enters the context of the LLM, who knows what the LLM might be doing on your system.